Hello everyone, I am Hilay Patel. Along with my teammates Naman Kalra and Vedvyas Reddy, we present our project titled PLC based aircraft autopilot system with HMI integration. This project has been developed as a part of Control and Automation Laboratory under the guidance of Dr. Sai Krishna. In this work, we have designed and implemented a complete autopilot control system using TIA Portal, integrating ladder logic, PID control, and real-time HMI visualization. The system is capable of controlling three key flight parameters like altitude, heading, and speed, using a combination of supervisory, discrete logic for safety and PID-based control for smooth operation. In this video, I will explain the system rung by rung and demonstrate its working through simulation. Here is the network by network explanation of our project. Network 1 is the main safety enable rung. The autopilot becomes active only when the master switch is on, sensor condition is okay, stable flight is available, and there is no manual override, no emergency stop, and no fault. The output of this rung is AP active. This is the backbone of system because if any unsafe condition occurs, AP active immediately turns off. Network 2 is the used for indication when AP active is on, the autopilot lamp is turns on. This helps the operator to confirm from the HMI or the output panel that the autopilot system is currently alive. Network 3 is altitude mode enable. Network 4 is heading mode enable and network 5 is speed mode enable. Network 6 calculates the altitude error using subtraction formula. The formula is altitude error is equal to altitude set point and the altitude act. This error tells whether the aircraft is below or above the required altitude. Network 7 is the altitude threshold detection. When the network checks whether the altitude error is outside the allowed deadband, if the error is greater than plus 50 feet, the aircraft is considered to be low, so altitude low becomes turns on. If the error is less than minus 50 feet, the aircraft is considered high, so altitude high becomes on. This deadband avoids the unnecessary elevator movement for small variation. Network 8 is the altitude persistence timer. Network 8 uses a T-on timer. The timer starts only when the altitude low or the altitude high remains active for 2 seconds. This delay means that the system does not react immediately to small disturbances or the sensor noise. Only if the altitude error remains the 2 seconds the correction is allowed. Network 9 and Network 10 is kind of elevator up and elevator down, which means it guides the aeroplane to move up or down. After generating the elevator outputs in Network 9 and 10, Network 11 introduces a correction counter for altitude control. This counter increments every time the persistent timer completes, which means a valid altitude correction attempt has been made. The purpose of this counter is to monitor how many times the system is trying to correct the altitude. If the counter reaches a predefined limit, which is 5 attempts, it indicates that the system is unstable and stabilize the altitude. This condition is treated as a fault, which later disable the entire autopilot system. Network 12 is heading error calculation. Now moving on to the heading control section. In network 12, the heading error is calculated as heading error is equal to heading set point minus actual heading. This tells us whether the aircraft needs to turn left or right. In network 13, we apply deadband of plus minus 3 degrees. If the error is plus greater than plus 3 degrees, heading right becomes true, and if the error is less than minus 3 degrees, heading left becomes true. Network 15 is heading timer and rudder output. After detecting the heading deviation in networks 13 and 14, network 15 introduces a persistent timer. The timer starts when either HDG right or HDG left is active and runs for 2 seconds. This ensures that the system reacts only to sustained error, not the noise. Once the timer completes, if HDG right is true, rudder right is activated, and if HDG left is true, rudder left is activated. Network 16 heading correction counter. Network 16 counts the number of heading correction attempts. Each time the timer completes, the counter increments. If the counter reaches 5, it indicates a repeated failure to correct heading, and this condition is treated as a fault. If heading returns within a range, the counter resets. After completing altitude and heading control, we now move to the speed control section, which is more advanced as it uses both discrete logic and PID control. Network 17 is speed error calculation. Speed error is equal to speed set point minus actual speed. Network 18 is speed low detection. If the speed error is greater than plus 5 knots, the aircraft is slower than required, so speed low becomes true. In network 19, if speed is less than minus 5 knots, the aircraft is faster than required, so speed high becomes true, indicating that the throttle must decrease. Network 20 is speed persistence timer. Network 20 introduces a 2-second timer similar to previous loops. The timer starts when the speed low or speed high is active. Only after the error persists for 2 seconds, the correction is allowed. This prevents unnecessary throttle fluctuations. Network 21 is counts the speed correction attempts. If the system tries 5 times and still cannot stabilize speed, a fault condition is triggered. After network 21, we move to the network 24. Network 24 is PID enable condition. Network 24 enables the PID control. PID is active only when the autopilot is active, speed mode is enabled, no fault is present. This ensures the safe and controlled PID operation. PID is three-step controller. Network 25 implements that PID. It takes set point and actual speed as input and calculates the control output using proportional, integral, and the derivative actions. Instead of analog output, it generates increase command and decrease command. Network 26 is final throttle output. The PID output is combined with the speed low and speed high and the safety enable condition. If speed is low, the throttle increment activates, and if the speed is high, the throttle decrement activates. Now we will move on to network 22 for the fault detection. The fault is triggered if sensor fails, manual override is activated, emergency stop is activated, any correction counter reaches 5. Once the fault becomes true, the autopilot is immediately disabled. Network 23 is fault alarm output. We have also integrated a watch table with this counter to reset the counter value. If a counter reaches 5 counts, then we reset the counter using the watch table. We have also integrated the force signals which are required and also the signals as data block 1 and the PLC tags. These are the PLC tags required in the project. We have also integrated the HMI connection root screen and the screen 1. The root screen is for the digital output and the screen 1 is for the analog output. I have simulated this root screen and I am keeping this image for a reference. I have forced these signals to keep autopilot active, and the autopilot active lamp is glowing. When the enable is 0, we get speed. When the enable is 0, we do not get any output. But as I have forced this value to 1, we will test these test benches. So when the speed set is 50 and the speed act is 25, the low signals comes as should come as 1, and the throttle increment should be 1. So as I'm doing this as 50 and this as 25, as you can see here, the slow signal is activated. So if I change from 25 to 45, threshold is 5. So exactly at 5, we did not get any output. If I keep 44, it will turn on as low. For the high case also, we can check with speed set as 25 and speed act as 50. As you can see here, the speed high is turned on. As now the speed control panel is working, now we will move on to the altitude control panel. As you can see here, the altitude set is 80 and when the altitude act is 10, we should make it down. We should also enable the altitude signal in the force table. As now I have forced this altitude enable signal, you can see that altitude set is 80 and altitude act is 10. We get the down signal. As you can see here, the down signal turns high. As the threshold here is 50, if we consider this case 80 and 80, we do not get any output. As you can see here, the down signal turns off. We can also do the case for the up signal. For the up signal, we will try this test bench as 10 to be altitude set and the 80 to be altitude act. You can see here the up signal turns on. Now we will move on to the heading control. For the heading control, the threshold is 3. So when I kept the heading set to be 10 and heading act to be 2, we will get the output to be right. You can see here the output comes as right. The threshold is 3, so if I keep this as 9 instead of 2, will do not get any output. As you can see, both the signals are turning off. For the left case, we will use this test bench for HDG set as 2 and HDG act as 10. We will get left as an output. As you can see here, the left turning on. You can see here, after doing the 4 cases for the speed control, the counter is counting till 4. So if I do it once more, it will create a fault signal. If the error adds 5 times measurement for a sensor, then the fault will come. As I have discussed, the counter is already counting till 4. So if I do it once more, it will create a fault signal. As you can see here, the fault signal is enabled. Now we will simulate this green one and check the PID controller. Here fault is already there, so we will remove it by watch table. As I have set this reset as true, all the 3 counters have been reset to value 0. Now you can see here the fault signal has been removed. This is the PID 3-step controller. Here the speed set signal and the speed X signal we can give and the error which is calculated by this PID is shown here and the corresponding throttle increment and decrement will be showed. So if I keeping this speed set to be 25, and speed act to be 10, the error should be 15. So as you can see here, the error is 15, which means the aeroplane is set at 25 but acting to be 10, which means the aeroplane is very slow. So we should increment the throttle so that it can move fast. We can also do the other part of this. As you can see, I have kept speed set to be 10 and the speed act to be 35, which means 10 minus 35 is minus 25. As you can see this error. So the set is 10 and the act is 35, which means the aeroplane is moving too fast and we should decrement the throttle. As you can see here, the throttle decrement signal is turning high.